Okay, hello and welcome to this talk in the LADAL Webinar Series 2022. My name is Martin Schweinberger, and together with Michael Hoare, I'm co-directing LADAL, the Language Technology and Data Analysis Laboratory in the School of Languages and Cultures at the University of Queensland in Australia. LADAL is a school-based support infrastructure for computational humanities that aims to assist anyone interested in computational or quantitative analyses of language and speech data. LADAL is part of the Australian Text Analytics Platform, ATAP, which is an open source environment that provides researchers with tools and training for analyzing, processing, and exploring text data. As such, ATAP aims to provide a powerful, customizable, as well as accessible toolset for a large number of researchers who have or who have not strong coding skills. LADAL is also part of the Language Data Commons of Australia, LDACA, which represents a national effort to make data accessible and fair. Before we start, I'd like to read out an acknowledgement of country, which we do here in Australia, to express respect and gratitude towards the Indigenous people of Australia. So I'd like to say that we as members of the University of Queensland acknowledge the traditional owners and their custodianship of the lands from which we are broadcasting this webinar. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections to country. And I'd also like to say that we recognise their valuable contributions to Australian and global society. Now, if you want to know more about LADAL and the resources we provide, please feel free to explore the LADAL website. No worries if you've missed any of our webinars. Almost all of them are freely available on our LADAL YouTube channel. You can also find information about past and upcoming presentations in the LADAL Webinar Series 2022 on the events subpage of the LADAL website. If you want to keep up with what's going on at LADAL, please feel free to follow us on Twitter or on Facebook. And if you have any questions, suggestions, or feedback, please do not hesitate to reach out to us by email. Now, without further ado, it's a real pleasure to introduce today's speaker, Bodo Winter. Bodo is Associate Professor at the Department of Linguistics at the University of Birmingham, a UKRI Fellow, a Leaders Fellow, a Fellow of the Institute for Interdisciplinary Data Science and AI, and Editor-in-Chief at the journal Language and Cognition. Bodo has received his PhD in Cognitive and Information Sciences from the University of California, Merced. His research focuses on multimodality, sound symbolism, gesture, and metaphor, as well as quantitative methods, specifically statistical modeling. So I'd welcome everybody, and especially our speaker today, Bodo, to his talk, Bayesian Generalized Linear Mixed Models with BRMS.
Perfect. Thank you so much, Martin, for this really nice introduction. And also, I want to thank you and the organizers for putting this amazing series together, but also for inviting me. And I feel very honored to be speaking here today. And I want to thank everybody there in the Zoom room for being here today. So I'm quite excited because I will be talking about Bayesian generalized linear mixed models, specifically implemented in the BRMS package. So to brace yourselves, prepare yourselves for about 60 minutes of a whirlwind tour that is going to be partially introductory, where I'm going to sort of review the basic core insights of the GLM framework so that we're all on the same plate. But I will also then sort of power through these things and at the same time problematize certain things that are happening in the field and reflect on, let's say, current statistical practice and what I see as some of the problems perhaps in statistical analysis. Before I start, however, I should say one thing, which is I need to thank Paul Bürkner, who's the developer of the BRMS package. So BRMS stands for Bayesian Regression Models with STAN. STAN is a programming language that is for Bayesian data analysis. And that is yet another programming language that you would have to learn if you wanted to implement Bayesian models. But Paul Bürkner did a massive service to the community by implementing an R package that uses syntax that's very familiar to our users and works as an interface with Stan, thereby making it really easy to fit Bayesian models. And I should say that in my own work, once I switched to BRMS over the last few years, it's drastically improved my workflow of data analysis. And I think this package is going to be one of the primary packages that's going to be at the forefront of making Bayesian data analysis available for more people. So just wanted to start out by thanking Paul Bürkner for his massive contribution to the community, making this so easy for us. Okay, to set the scene, to sort of frame everything I'll be talking about, I want to talk about 3 big shifts in statistical modeling in our field. Now, different people would make different choices about what they think are the most important developments. But to me, one of the most important developments is that we have moved over the last few years towards open and reproducible research methods. And in fact, this is one of the reasons why we use tools like R, because they're open source and freely available, and they allow us to then share data and code, and other people can trace our analysis if you're making that available with your publication. And I think that's probably one of the most important shifts in quantitative methods over the last 10 years. But there's been another shift towards parameter estimation-based approaches. An increasing recognition that rather than just using a prefab test like t-tests and ANOVAs and so on, we want to build a statistical model that estimates parameters, and we want to quantify the uncertainty we have in these parameter estimates. And that's a pretty big shift. I would say that one of the milestones in this was the 2008 book by Howard Bayesian, Analyzing Linguistic Data, which was one of the first textbooks to really emphasize statistical modeling above and beyond just significance tests. And these days, more and more people are doing parameter estimation within a Bayesian modeling framework. In many ways, I actually think that the Bayesian framework is sort of living up to the promise of having a nice statistical model that estimates all the parameter, a model that could plausibly have generated the data. So to me, the Bayesian approach is sort of the natural conclusion of this trajectory that we've been on towards more statistical modeling. But very briefly, I want to show you how some of the stuff that I will talk about later interacts with open science and reproducibility. And so I just want to briefly comment on this before I spend the rest of the talk on the latter 2 points. So as many of you may be aware, there's this so-called replication crisis, or more positively, the credibility revolution. Where it's been found, especially in neighboring disciplines like psychology, that many studies, when different researchers try to replicate the study, that they failed to find the same results. And what you see here is a massive replication attempt of hundreds of studies from a major psychological journal, where this is the replication effect size and this is the original effect size. Ideally, they should all fall on a nice line. But actually, you can see here that many of the original effects that were really large turned out to be really small on the replication. And the red dots are results that are not significant, showing you that many of the findings that people took for granted all of a sudden sort of dissipated. And the replication crisis is multi-causal, so we cannot pin it to just one thing. And there are many different things that we can do to change things. But statistical modeling and how we treat statistics is part of this crisis. It's one of the many causal factors of this. We're doing better by making our data analysis open, but I would say that prefab significance tests, so things like t-tests and ANOVAs, chi-square test, they are often taught within an incentive system in which we're trying to achieve significant results, and sometimes at all costs. This is no blame game. So just to pick an old slide of mine from when I was still teaching significance tests, which I think we now don't need to do anymore. I had this slide, which is like if the null hypothesis is false and you reject it, so you get a significant result, then yay, so sort of telling students already, you should get a significant result. And I certainly grew up with the expectation that this is what I should find. And in fact, here is another textbook. This is a textbook for linguists, a statistics textbook for linguists that says that if P is smaller than an alpha threshold of 0.05, for example, then you reject the null hypothesis and you congratulate yourself. And you can see how this is sort of creating an incentive system where you're looking for effects and where the primary outcome of an analysis is significance, rather than sort of reasoning about your theory, reasoning about a statistical model that could have generated the data. And this is the problem with this hypothesis testing world. And you see flow charts like this, which give you an aura of objectivity in the sense that there's this sort of dedicated procedure. And we have to recognize that each one of these significance tests, of course, as their primary goal is significance. And so what I want to talk about today, and I see Bayesian modeling as a sort of part of that tradition of this shift away from having the implicit goal of achieving significance towards a completely different goal, which is not actually to test any hypothesis at all in the first place, but to build a theoretically motivated model that could plausibly have generated the data. And that's a really big shift, actually, in how we think about statistical modeling. And then within that model, for parameters of interest, we assess the range of plausible values given model and data. So for example, if I'm doing an experiment and I have two conditions, maybe I want to look at whether people are faster in this condition and in this condition, then my parameter of interest is a reaction time difference between these conditions. I want to know what is the plausible range of reaction time differences given my specification of a theoretically motivated model. And so that's quite a big shift of emphasis. And I think it's not actually, even if we're using mixed models, LME4 and all of those, I think there's still a sort of tendency to think of the hypothesis test as the ultimate goal rather than as the goal of sort of building a model that is plausible. Okay, so I want to move from this consideration to parameter with estimation with uncertainty. And to sort of give you an example, and some of those of you maybe like there are people who have been at the workshop in Tromsø may know some of these examples, but in the 1997, there was a horrible flood that happened in North Dakota and Minnesota, the Red River flood. And it's a great example of how uncertainty in estimates is something that is important to consider. So specifically, the government released a forecast that the flood would come in at 47.5 to 49 feet. And people, in response to this forecast, the local government officials built 52 feet dikes. And that would seem to be a sensible choice, given, depending on how you interpret that range that was given to you. What are these numbers? What do they mean? Is this a confidence interval? Like, what is this actually a number of? But then the flood came in at 54 feet and swarmed everything. So the reaction to the forecast was off. And this is partially based on a misunderstanding or sort of not dealing with uncertainty the right way. So if we think about it, that forecast, there's a range of plausible values that the flood could have come in. So the parameter of interest in this case is the height of the flood level. And if you want to build a model of that, the outcome of that analysis will be a distribution of plausible flood heights. Yeah. So it could be 48, but it could also be as high as 53 in this particular example. And then if this is the parameter that we're estimating, yeah, so the height of the flood, we are building things that we know about our study system, in this case floods, into our model. So for example, we might tell a model, oh, floods vary as a function of temperature. And if that's the case, now that the model has known about this variation, in this case, sort of sequence temperature variation, maybe your range of plausible estimates changes, because now the model knows about a new source of variation and correspondingly adjusts its uncertainty. And it's perhaps now, in this case, in this example, more uncertain. And things might differ based on spatial variation. And that too might change the range of plausible estimates. And the idea that I sort of, the conceptual framework that I want to propose here is that if we think about parameter estimation, here we're modeling the parameter of the flood height. We want to incorporate as many sources of variation that we know could influence that estimate. And we don't want to hide variation from our model because we want to propagate the variation in the data so that the model is sufficiently uncertain about that parameter of interest. And if we think about it, this is a great example of a situation where the range of plausible estimates is really where it's at. That's relevant to us. Here, I'm just zooming out and showing you 0. Well, this is sort of akin to doing a significance test on these flood level estimates. So if you're saying, okay, we have a significant flood height, in this case, this would be really odd and not really tell you anything. The only thing that you could say is that the flood would come in potentially at not 0. But it's a great example of how sometimes actually the null hypothesis isn't as interesting, and it's not the main thing that we should be testing for. We should be interested in the range of plausible estimates, and just that it's different from 0, or that the data is incompatible with the assumption of 0. That's not necessarily what we are always interested in. Okay, so the workflow that I'm proposing here is that you specify your model before you see the data. You could then also pre-register this analysis. If you know enough about your data, you can specify your analysis plan and make it public. But regardless of whether you do this, you build a theoretically motivated model before seeing the data ideally. You show the data to the model, and then that model will then be estimating the parameters based on the data that you have specified, or the data that you're giving to the model. And this is a sort of step that is more specific to Bayesian data analysis. You then let the model, once you have the model fitted on the data, you then let the model simulate new data. You'd say, okay, given that my model now knows about the data, given these specifications, could that model have generated the data that I have? And if it couldn't have generated that, that's a sort of basic test to say, well, that is not actually a plausible model that captures the major trends in this data very well. And so this then means that potentially you might have to revise the model if your model cannot simulate the data. And this can be a sort of loop back and forth. So model checking from this perspective is an integral part of good statistical practice. Importantly, none of this is done with respect to, you're not checking things with respect to your hypothesis. You're just checking whether the model could have generated the data. You're not making modeling decisions contingent on whether your hypothesis is supported or not. And from this perspective, the distinction between confirmatory and exploratory sort of breaks down because you're intrinsically, while you are starting with a confirmatory model that you have sort of envisioned based on your understanding of your linguistic data set, you might have to revise that if the simulation of new data does not actually converge at all on the data that you have. I'll make this more concrete later on. And then as a final step, you perform inference on the population parameters of interest, or you can test hypothesis. But crucially, this is the final step that's done within the model that plausibly generates the data. So it's the last step rather than sort of significance tests, which put this as almost as the first. I mean, of course, they also do parameter estimation, these things, but conceptually, it's the primary goal with significance test. And here, in this modeling workflow, it is not the primary goal. The first goal is to have a plausible data generating model. Okay, so this is just the overall workflow. Let's make things more concrete, and let's do a very sort of quick review of the generalized linear model framework, and sort of then see in more detail how this pans out also with linguistic examples. So Many of you may be familiar with the normal distribution, which, let's say you have a study system and you have some data. Let's say you're modeling voice pitch in a phonetic study. If that was the case, then you can say, okay, let me assume that the process that has generated these voice pitch values is normally distributed. And here I'm showing you 3 different normal distributions with 3 different parameter configurations. So mu, the mean, is equal to 0 over here, standard deviation equal to 1, a lower mean and a lower standard deviation. So the mean gives you the location of the normal distribution and the standard deviation, the spread. So the normal distribution has 2 parameters, the mean and the standard deviation, mu and sigma. And so if you say that I assume that my data has been generated by this distribution that you're seeing here on the slide, then my goal is to estimate these parameters from the data. So the idea is that we have all sorts of distributions that our data could come in, and these are empirically observed distributions, and we're using theoretical distributions that we assume could have generated the data on the left-hand side. And these are sort of these mathematical monsters. They are pre-specified in the sense that we know their properties. We know formulas for these different distributions, and we can then say, well, we can use the empirically observed distribution to estimate parameters of the theoretically observed distributions, which then also means that it's a two-way street, because that means then that we're assuming that the theoretical distributions are the appropriate data generating process. So they are underlying the distributions on the left-hand side. And so then from this framework, then a lot of what it means to be a good modeler is also to be familiar with these different distributions and sort of recognize their general shapes and what types of data they might be appropriate for. And I should say that real data never is normally distributed or Poisson distributed or any of these. When my students say, oh, my data isn't normally distributed, I always say it isn't anyway, because the normal distribution is a mathematical abstraction that you're using to describe a particular empirically observed distribution. Okay, so how does this map onto statistical modeling then? So linear regression is a model that assumes a Gaussian or normally distributed data generating process. So let's say we have age on the x-axis, we have voice pitch on the y-axis, and if you're a phonetician, forgive me that I'm using pitch here. I know it's fundamental frequency, but it's to keep the example simple. And then we have different data points, let's say each one from a different person here. And what you can see here, if you do some squinting and some wishful thinking in this plot, you might see that there seems to be a linear relationship where as people get older, their voice pitch drops in this particular data. And this is a nice model in the sense that it captures the major trend and sort of gets rid of a lot of the detail of the noisiness and is useful for us in that sense. In R, we would specify it like this. Probably many of you are familiar with this. LM for linear model, pitch as a function of an intercept and age. But also, if you're doing this the Bayesian way, we're not going to do anything particularly Bayesian with this right yet, but actually you just have to swap LM for BRM, because that's the beauty of BRMS. It models the syntax that we're familiar with. And so then we have an intercept. One is just the notation that's used here as a placeholder, and a slope, and they are the two main characteristics of the line. So the slope tells you about, for each increase in age by 1 year, you have to go down by minus 0.7 hertz. So you'll drop by 7 hertz over 10 years. And then we have the prediction for age equals 0, which is the intercept. So that is, you can think of it as the sort of starting point of the line or the height of the line. And that is the value where this line crosses 0 on the x-axis, where basically it is on the point where it intersects the y-axis. Okay, so crucially, this model that is standard linear regression is underlying a model that assumes a normally distributed data generating process. So essentially what you're doing is you're modeling a shifting mean of the normal distribution. So a mean that is now conditioned on the age predictor. The normal distribution changes as a function of age along the y-axis. And it has the same spread because in this model, we're not allowing the spread to change. We're just allowing the normal distribution to shift along this predictor. And so we could note our model down like this. We have our y's, which in this case are pitch values, are drawn from the normal distribution. So I like to think of this tilde as sort of drawn from, randomly drawn from, or the normal distribution generates our values, our y values. And that has two parameters, the mean and the standard deviation. And this essentially is our assumption about what distribution could have plausibly generated the data. And then we have the equation of a line. So here our mean is the intercept. So this is just a placeholder. This is the notation, the mathematical notation for the intercept, plus a slope times my predictor. So depending on what age values I plug in here and depending on the strength of the slope, I will get different values. And so how do these two things correspond to each other? Well, that thing, that entire equation of the line predicts the parameter of interest, the mean of the normal distribution. So we call this the linear predictor. It is literally the equation of a line. It's a linear combination of different additive terms. And that models our mean, and therefore we allow the mean to depend on our axis. So another way of noting this is to introduce here a sub-index where I say, oh, we have different means, mu. We just said, let's say Martin. If Martin is I equals 1, then depending on Martin's age, I would plug in a different x value that gives me a different mean. And likewise for myself, I would plug in that value and would get a different mean then. And what's nice about this framework is that it readily extends to, for example, categorical predictors. So the x does not have to be continuous. For example, if you had young versus old age differences, you can pretend they're on a coordinate system. And in this case, then the x becomes an indicator variable, which if it's at 0, you have the prediction for one group. And if it's 1, you have the prediction for the other group. So it's like a switch where you say, let me add an increment based on whether somebody is old or not in this data set. But crucially, that is still a data generating process that is assumed to be normal. So we're having a shifting normal distribution, one normal distribution for one group and one normal distribution for another group. And this, of course, extends. And the idea then is that anything that you know about your study system, anything that the literature suggests, any theory can be incorporated to basically make this mean depend on multiple different things at the same time. Okay, but so this is, we're going to get into mixed models in like 5 minutes, but this is just for data that can be assumed to have come from a normal distribution. And what if that is not the case? In many cases, we know before seeing the data that it's impossible for the normal distribution to have generated the data. And so as linguists, of course, we deal with a lot of discrete or categorical data. One of the distributions that we can use, in particular, if we have two binary cases, like, for example, modeling whether a participant responded correctly or incorrectly, or whether there is a dative or a different type of construction, then we can use the Bernoulli distribution, which is the coin flip distribution, a subform of the binomial distribution, a specific instance of that, where basically we just have the probability of an event occurring. So let's say the probability of a dative occurring being 0.8 or being 0.5, and then you get half of each. But this has one parameter, the probability. So this distribution, the Bernoulli distribution, only has the probability, and depending on how you turn that knob, you get different values. The same way that if you turn the knob of the normal distribution, you get different means. And so if this was our previous model, we have family equals Gaussian, because that's the assumption about the data generating process. Then what we want to do is we want to put in family equals Bernoulli, because we now cannot assume our y's to be normally distributed if they're categorical. So if you're modeling accurate or inaccurate responses. And ideally, we would like to do something like this. Please don't take a screenshot of this yet, because this is wrong. But we would like to say, okay, our y's are generated by the Bernoulli distribution. Yeah, so they are either of one type or of another. And we have a probability that determines this. And we want this probability to depend on some predictors. So we have a linear predictor as well. But the problem is that the equation of a line, a line will inevitably at some point cross 0, and it will inevitably at some point cross 1. But probabilities, a parameter for this distribution, can only be between 0 and 1. Yeah, it makes no sense to have a probability of -3. And so this machine would ultimately crash because the linear predictor can predict parameter values that are impossible. Yeah, values smaller than 0 and larger than 1. And so we introduce a mathematical trick, the logistic equation, which is an equation as a sort of scrunchiness function. And what it does is it takes the output of this predictor and makes it so that it can only be 0 and 1. Yeah. And now I have plausible p's, and then I draw from this something that's either a y is either 1 or 0. Yeah. So crucially, the y here is categorical, but the parameter is continuous between 0 and 1. Okay, so that's then logistic regression, which is a generalized linear model that assumes a Bernoulli distributed data generating process. And now a final version of the generalized linear model that I want to discuss, which is probably the generalized linear model that I use the most, because I deal with a lot of count data, and the Poisson distribution is a sort of natural go-to tool for a lot of different types of count data. So for example, if you have this is the distribution, the Poisson distribution for a particular mean of 0.5. So what that means is that if the underlying parameter of this distribution is 0.5, then you would get mostly zeros, yeah, about 60% of the time. Sometimes you get ones and sometimes twos and so on. So for example, you might use this to model the rate of gestures that you observe. And if the rate is 0.5, then most of the times you will get 0 gestures, sometimes 1, sometimes 2. And this is the Poisson distribution for a different parameter, 4.2. That's a higher value. And that means then that you expect higher values, but ultimately the outcomes are positive integers. Yeah, they're just 4, 3, 5, they're distinct, discrete values. But the parameter is a continuous mean of observing this count data. And crucially, this is unbounded. I'm only showing you this for the 10, but this is sort of, it extends towards infinity. So this distribution has only one parameter called lambda, and that is just the mean of how many counts on average would you observe. So where would you use this Poisson distribution for? It comes up quite a lot in linguistics whenever you have an unbounded count process. So many word frequency data sets are like this, because you can model word frequency data if you don't know how many words could occur in a text. Or gestures. So I count gestures a lot. And so I might be interested in whether gestures depend as a function of speaking context, whether people use more gestures when speaking politely or informally. Well, then what I would do is I would model a different lambda, which gives me different underlying gesture rates. But crucially, the values of gestures that I observe will always be discrete valued of gestures. So if this is our distribution, and again, please don't take screenshots of this because this is not correct yet, we want to do something like this. We want to have our lambda, our rate of the Poisson process, of the count process, draw from or be influenced by our predictors. So that, for example, I can look at whether different politeness conditions influence the mean rate of gestures. But this machine will also crash because, again, lines can be negative. They will at some point cross the zero threshold. So we wrap the exponential function around it, because similar to how the logistic function makes everything into 0 and 1, the exponential function, if you exponentiate anything, it will always be positive. And so this way you can make sure that your linear predictor is linked to the parameter in such a way that only plausible parameter values can be predicted. And the y's will be positive integers, yeah, like 3, 2, 6, and so on. No in-betweens, but the lambda will be a continuous parameter of how many counts will you get on average. Okay, so this is just a very quick overview of the generalized linear modeling framework. It's parameter estimation, where we're modeling different parameters depending on what distributions we think underlie the data generating process. So linear regression, logistic regression, and Poisson regression, they're all different types of generalized linear models. They all have a linear predictor. Then they have an assumption about which distribution has generated our y's. And then they have a link function that links the predictor to the parameter of interest so that you only predict plausible parameter values. And yes, the linear regression also has a link function in this framework, the identity link, that's this I bit, just to make sure that we have this nice parallelism. This function basically does nothing, but therefore we have a link function in each one of these cases. Okay, so now let's move very quickly for about 10 minutes to mixed models, and then we'll talk about some of the more Bayesian bits of this. In a recent paper, so generalized linear models are a subtype of mixed models, and they're basically mixed models without random effects. But if we add random effects, we then call them mixed models. And one of the reasons why mixed models have sort of taken linguistics by storm is because we have so much nested and clustered data. So far, I've talked about putting predictors into your model, but your model needs to know about these different sources of variation. So for example, that different people are different from each other. So participant and item are a source of non-independence in your design. So if you have multiple data points from the same participant, you cannot exchange these data points anymore. They are now tied to that individual, and your model needs to know about that individual, because otherwise, if it doesn't know about the fact that your data comes in clusters, your model will almost always be biased. And so participant and item are sort of standard random effects in psycholinguistics, social linguistics. Many different fields have random effects for these. Language and dialect, if you have multiple data points from the same language, then you need to account for the fact that they are all mutually dependent. In a social linguistic study, this might be dialect. Then if you have a typological study, you might have language family as a random effect, because different languages from the same family are clustered and they are going to be more similar to each other because they have a shared history. And if you cannot treat these languages as independent anymore, you need to account for that source of independence. And if you are doing corpus linguistics, well, corpora are massively hierarchical clustered structures. So, for example, you have files within authors, within registers. And the thing that we discuss here, where we sort of in this paper review random effects across different areas of linguistics. So I think this works nice as a sort of introduction to how mixed models are used in different fields, including some sort of more unusual random effect structures. One of the things that we argue for in this paper is that corpus linguistics needs to bring even more structure of the corpus into their mixed models by having even heavier random effect structures. Okay, so, but importantly, random effects, just adding a random effect for participant and item does not do the job of accounting for the independence assumption of our tools. And importantly, we need to think about random intercepts versus random slopes. And this is super, super crazy important because actually most of the time, random slopes is where it's at. So let's talk about this. Let's say you had a trend where across trials, people would get more accurate. Yeah. So here I'm showing you the population average. And then I have a line of this, so we can forget anything about GLMs for now. We're just gonna look at this sort of conceptual case where we have then an intercept here where the accuracy, which is the prediction for a trial of 0, yeah, which is just where this line crosses the y-axis. And if we then say, let's add random intercepts to this model, then this would account for the fact that maybe you have multiple data points from the same participant. And if that's the case, some participants might be overall more accurate and some participants might be overall less accurate. And that's what the random intercept term would model variation across subjects in the random intercept, in how much this line goes up or down. And so these lines are separate lines for each individual. If we then add random slopes, we allow the trial effect to vary as a function by accuracy. And you can see why it can be very dangerous to not have a model with random slopes. From a conceptual perspective, if you don't have random slopes, you assume that the trial effect is constant across individuals. That's a very strong assumption to make. The idea that like everybody would increase accuracy exactly the same way. And that's theoretically often not motivated. And so moreover, if you're hiding this variation of lines affects your uncertainty in where the average estimate for the line is. And hiding that variation from your model means that its inferences might be severely biased. And in particular, your confidence intervals, or in a Bayesian context, your credible intervals, might be artificially narrow because you're hiding the variation from your model. And that happens when you don't have the random slopes in your analysis. And so if you look at these cases, accuracy as a function of intercept and slope here, then with random intercepts, essentially what we're doing is we're allowing the intercepts we're conditioning those for separate individuals now. So maybe, I don't know, Martin gets a higher intercept than myself, gets a lower intercept, and we're modeling variation across intercepts. And then for the final case, we are then also modeling a separate variation term, a standard deviation in slopes. How much do the slopes vary across individuals? And that is variation that we should probably not ignore. So standard notation for this is GLM in sort of the standard significance testing world, GLMER for generalized linear mixed effects regression. And the notation then is that the pipe here means that the one is conditioned on a subject. So different subjects are allowed to vary in their intercepts. And if you then add random trials, then the trial predictor is also to the left of the pipe, part of the variation across subjects. And in BRM, in Bayesian regression model context, you would have the same notation for each one of them. And you can specify your model just as you used to from packages like LME4 and so on. So the core logic of the generalized linear model framework is very similar. Okay, so importantly, we know, and there's been a lot of literature on this, that models with random intercepts only, if there is actually a warranted, if the data actually suggests that there should be that there is variation in the trial effect, if you're ignoring that variation, these models tend to be sometimes grossly anti-conservative. And this has been known for a long time, even before those discussions sort of went into linguistics. So this is sort of, I sometimes get the impression, and I think that more and more people are now aware of this, but a lot of the times it seems as if people assume that if they just have a random effect for participants and items or something like that, that the job is done. But to me, in many cases, not having a model with random slopes is almost sort of going against the purpose of using a mixed model to begin with. And Richard McAlrath, in his book Statistical Rethinking, which is sort of one of the new Bibles of Bayesian data analysis, says that when it comes to regression, multi-level regression deserves to be the default approach. And this is somebody who's very much against defaults, and he still says this. I think in linguistics, almost everything, if you're modeling one response, if you're having these types of models, almost everything needs to be a mixed model because we almost always have clusters. But importantly, these models need to take the random slope variation into account if it is theoretically motivated, if we cannot assume that people have the same trial effect. Okay, so the problem then is in the field that people then build a model like this, and then it doesn't converge. And then it crashes, So basically no stable estimates have been found. There's no unique solution. So the likelihood estimation procedure that is used to estimate these models hasn't found a stable solution. And then what people tend to do is to immediately move towards the simpler model structure. So they say, okay, I cannot fit the random slopes, therefore let me move to the simpler model structure. And this is really widespread in our field at the moment. I see this a lot as an editor and reviewer. There's also a paper by Lotte Mettiard, which has recently sort of done a nice review of researchers, and 75% of all researchers who have used mixed models in the study report to have uneasiness about certain aspects of the data analysis. And one of the primary things that they mention is convergence issues. And I've certainly found this across the board with people. With my students and so on. Now, how do you fix convergence issues? So like this is basically the convergence issues means that like you cannot estimate the parameters that you're interested in particular, often the random effects parameters, given this data set. And the thing is that there's loads of different solutions to this problem, but they're all sorts of hacked sometimes. They require a lot of investigation and troubleshooting. And so Brouwer and Curtin have this long list of convergence issues fixes in their paper, and I like that list in principle. But some people say, well, actually, maybe we should, rather than sort of trying to hack something, and certainly not simplify a model as the first solution, maybe move to an approach where the estimation is more robust anyway. And that happens to be the case with Bayesian models, which since I switched to Bayesian models, I haven't had a convergence issue that I couldn't deal with because of the different ways in which they're estimated, and also because priors can sort of help you with the estimation process as well. And so rather than teaching this sort of hacked solution of lots of different ways of coding around this, and in particular, rather than simplifying our models, we should be sort of incorporating, I suggest switching to Bayesian models because they're much more robust on this front. And actually, this was, at the beginning, I wasn't a Bayesian sort of person in theoretical leaning. I mainly switched for pragmatic reasons because my models didn't converge. But since then, I've realized the many other advantages of this framework. So I want to give you a quick example of a model that sort of incorporates a lot of this that showcases a more complex random effect structure and how this would look like in BRMS. And my timer says I have talked for 45 minutes, so I'll talk for 15 more minutes and I'll get to the more Bayesian bits very quickly after this. So this particular model that I want to talk about is a corpus analysis. And it's based on a really cool new paper by Gabriel Adams and colleagues, which talks about the fact that in English cultures, there seems to be a bias towards addition and neglecting subtractive solutions to problems. So for example, in one of the experiments, they asked participants, here's a sandwich recipe, can you improve this? And people, when they asked, improve this recipe, they will almost always add a new ingredient rather than subtract one. Or in a very basic way, if you have to make this display symmetrical and you can either take a green dot away or you can add a green dot, people will tend to add 3 green dots over here to make it symmetrical rather than take these ones away. And that's even if they have to pay extra money for each of the dots that they add. So it's a very sort of low level bias. And in this paper, we wanted to look at whether this bias towards addition and subtraction has reflections in language statistics. So we're looking at all sorts of things in here. The paper is much more complex than the small sub-result that I'll just talk about. But one of the most basic things is to look at how words related to addition or the concept of more, whether they're more frequent. And so we have words like this: add, subtract, addition, subtraction. Each one is of a pair because they're sort of like two members of the pair. And then here I'm showing you frequencies, word frequencies from COCA, but ultimately these are aggregate frequencies, and they collapse the entire nested structure of the corpus into just one number. So we cannot trust these numbers because they ignore the clustered structure. So I want to know whether this frequency depends on type, but I need to account for the fact that some pairs have a much bigger frequency difference, but then I also need to account for the internal structure of the corpus in this as well. And so this is the model that we have specified in this particular analysis. So let me walk you through some of these components, and I'm not going to have a lot of detail, but I will give you also sort of pointers to tutorials where you can get help on these things. But so this bit down there, which looks rather scary, some of those commands you could actually omit. They're not particularly necessary. But this is all to control the convergence. So this is MCMC, Markov Chain Monte Carlo, is the process by which these models are estimated. All you need to know for the sake of this talk is that just like linear mixed effects models, they're estimated using a numerical estimation procedure. And here you can tweak the parameters of this numerical estimation procedure to make it more likely to find a stable solution. And this looks really scary, but one of the good things is that the BRM package, if it doesn't converge, will give you a very clear warning message that says, change, for example, adapt delta and put it to a higher value. And it will actually give you very clear instructions, which is very different from having to cope with convergence issues in linear mixed effects models, where often you get these quite obscure error messages that are hard to interpret, and then you don't know how to deal with them. So I should say that even though this looks scary, actually, you will get a lot of help from the package itself. Then over here, we have the family specification. So our specification about the underlying data generating process. And so this is open-ended count data. So we could use the Poisson distribution here because that is a sort of go-to tool. But the negative binomial is a close cousin of the Poisson distribution that allows, that additionally models the variance, because some data might be over-dispersed. It might have more variance than what is expected. Either way, I should say, this is a type of model, this negative binomial model, is a type of model that you cannot actually easily fit in a mixed way using the widely used LME4 package. So there are more model options available for BRM, and you don't have to switch to a new package. So for example, if you have ordinal data, like Likert scale ratings, right now, if you want to do that in a mixed context, you need to switch to something like the ordinal package from LME4. In BRM, you can do this all within one framework. Then we have prior specifications here, which I will talk about in a second. And then here is our main fixed effect. So we want the frequency to vary as a function of whether the word is of the type addition or the type subtraction. And then we have an item random effect, because some items might have bigger addition effects than others. And notice that importantly, this is with a random slope. And I'm bringing in as much of the corpus structure that I have in the metadata available to generalize over the clustered nature of my corpus. So in this case, we have multiple occurrences of the same word from the same file. And within the same file of the corpus tends to be similar type of text. So that's one sort of hierarchical cluster. And then we also decided to incorporate register as an additional random effect, because maybe in certain registers, like maybe academic language, the addition effect might be amplified. And we want to estimate variation of the addition effect across the different registers. And importantly, for corpus linguistics, of course, it has always been important to sort of model dispersion and model and think about the fact that a certain text might introduce a bias, and maybe the word addition is super frequent in just one text, and that biases your overall results. But crucially here, the idea is to bring that structure into the model as sources of variation terms. I'm going to skip this bit, which was a nice example I wanted to discuss, but I have no time because I want to get to the Bayesian bits a little bit more. So I have about 10 more minutes, and I realized that I timed this really badly. But everything that I've already talked about essentially is sort of Bayesian in spirit, but now I'm going to extend this to the more Bayesian bits. So the one thing that scares a lot of people when they move towards Bayesian data analysis is the fact that you have to make prior assumptions about where you think the parameters lie. And this is something where then a lot of people say, like, oh, I don't know where exactly are the values of my that I expect my parameter to be in. And the reason why you have to do this is sort of explained by this meme, which is that the primary outcome of Bayesian data analysis, which is the posterior distribution, which gives you an indication of what are the plausible parameter values given my prior and given the data. You need the prior specifications to get that nice panda down here. Both of those are part of a base formula, which I'm showing you here in simplified version. So we're interested in posterior estimates, which is basically how much your model had to adapt its priors after having seen the data. And that results from multiplication of prior times likelihood. So your prior expectation about where you think your parameters lie, and the likelihood is generated from the data. And this means proportional to. The actual equation is a bit more complex, but this is the core insight, everything that matters to us sort of applied data analysts. And I like to show this with Seeing Theory, which is a really nice online tool that I highly recommend you to have a look at. It has sort of like, it's also really good for teaching, has all sorts of like animated visualizations. However, in the interest of time, I'm not going to show this, but I recommend you to look at chapter 5, which has sort of animated visualizations where you can put in different priors and then see how that affects the posterior when you sample different data. It's a really useful tool. So this prior to posterior thing is a really good way of explaining this. What I'm going to focus on is specifically priors for the coefficients of your model. So for the intercept and your slope, or your many different slopes. So the idea is that we want posterior estimates of our coefficient values. So we want to know what are plausible slopes, and we put in prior information about that. But we're going to focus first on the posteriors, because that is the sort of thing that also matters in how you communicate your results. Thinking about not just one H-slope that is suggested as the best H-slope for your data, or whatever's one condition effect, like just a point estimate, but instead thinking about a range of values given your data and given the priors. So what I've shown you in this graph before, these were actually posterior means. They were point estimates, but behind them lies a whole range of plausible slopes. There are different slopes that are compatible with this data. It's possible that the slope might have been slightly different. And so what I'm showing you here is the posterior distribution of the age predictor slopes. So these are all the possible slope values. You can then see that, aha, it could be as low as minus 0.5, which is not as steep, but it could also be as deep and steep as minus 1.0. And it's this posterior that is sort of one of the things that you focus a lot on in Bayesian data analysis as the thing that you interpret and communicate to your audience. And this is the posterior of the intercept. The same way that you have different plausible slope values, you have different plausible intercepts. And what I'm showing you here is the distribution of both intercepts and slopes. So this is all the plausible intercepts and slopes given my model and given the prior information that I've put into my model. So each point in this plot, so basically this distribution here is just sort of one version of what you've seen from this big distribution here. Each point in this plot is a line. And each one of those lines is a different line that is compatible with my data. So rather than saying I'm just looking at one point estimate and test that against 0 in a significance test, I'm looking at what is the range of plausible slopes and intercepts given my model. And so a more natural way of sort of visualizing the uncertainty here is that the line could have been any one other line of my posterior estimates. So I have variation in these lines. And that's a sort of more Bayesian way of simulating, like looking at the uncertainty of my data. All of these are plausible lines. Okay. So that is the thing that you focus on in the interpreting stage, the sort of posterior distributions, but how do you get them from the data? And in particular, we're not going to talk about the mechanics of how that works in detail, but in particular, how do you make good choices about priors? So one good news is that BRMS, the package, actually comes with very sensible choices to begin with. So not saying that I recommend to do this, but if you were to just use your mixed model and just flip the notation to BRM, you would be fitting a Bayesian model without having hand specified the priors. And a lot of those choices are reasonable. And you could then report those choices that BRMS made for you. But the one thing that I want to talk about where you actually have a really good influence on your data analysis is weakly informative priors. And specifically, we should be concerned about overfitting, which is learning too much from our data and constraining our models too much to our data, versus underfitting, sort of not putting in enough information into our models. And we have to sort of find that path between the Scylla and the Charybdis in the Greek mythology. I'll talk about this in 1 second, but overfitting is one of the things where we can actually use priors to sort of help us learn more slowly from our data sets. So this might be a prior that you put on your slope estimates. This might actually be a sensible prior even for the pitch values. So I show you different priors here. So this is a normal distribution with different standard deviations. And it's crucially centered at 0. So the basic assumption is that you're putting in 0. And what that means is that your model will assume that 0 slope is the most likely value, and it will be slightly drawn to this. It's possible to detect an effect over here. If there's lots of data, it will say, okay, yes, I believe there's actually evidence, even though my prior was focused on 0. But I'm sort of building in mild skepticism or a conservative assumption. And then the question is, what is the range of plausible effect sizes that you could expect? And you often have some ideas about this. For example, in reaction time studies, 300 milliseconds would be a massive effect. So you want to have a standard deviation that is probably sort of more narrow than that. But crucially, this decision is made based on past literature and information you have about your analysis, and it makes your analysis more conservative and learn more slowly from the data. And if there's a really extreme slope that's suggested by the data, it's going to be a little bit more conservative and say, I should be hesitant, and I'm building in more 0 sort of information. And that's partially also to, in particular in linguistics, where we have small samples that we know are biased in their effect sizes, putting in weakly informative priors on coefficients in particular is a good thing to do. So I have about 2 more minutes, and I realize that I'm unfortunately mistimed some of this. But I just want to briefly say a few things about like these prior choices. They're often a point of contention where frequentist people who are used to sort of the, in particular, null hypothesis significance testing as one version of frequentism. People think that prior choices are like the Wild West. But importantly, as you've seen in this example, you're not going to put in an effect. You're not going to say, I'm going to assume that I have this really strong effect here, which would be sort of cheating, but you actually put in a conservative assumption. You could say that frequentism is to some extent the Wild West because you're also making lots of choices, but some of them are not explicit. So frequentist models essentially conceptually assume that any value is equally likely, and they will be exclusively driven by the data at hand and not as skeptical of the data than a Bayesian models with the appropriate specification. And Bayesian models with regularizing priors then will always be more conservative. And I would say a lot of our mixed models and a lot of the things that we've seen in literature trust the sample too much, and we need to build in more skepticism towards the sample. And there's, in a wider sense, always a heap of assumptions. Even if you're doing a significance test and so on, it's not an objective procedure. It's actually still bound up with whether you've excluded the data, transformed it, and so on. Okay, here's a nice quote. Complaints about the subjectivity of prior choices distract from the fact that they're subjective choices made during every step of statistical analysis. Okay, I realize that I've completely run out of time, but I want to say to you that remember this simulating data step. One of the nice things is you can wrap this PP check function, which then is simulating new data given your model, and each one of the blue lines is a simulation of new data, so new voice pitch values, and you can see whether the actual data falls within this to actually assess with the Bayesian model whether it is a plausible data generating, it has correctly identified the data generating process. And it's a very nice thing where all you need to check is the black line, the real distribution within the blue distribution. Okay, I'm going to very quickly go to my wrap-up slides. And tell you, so some of the reasons why I prefer Bayesian models. I've already talked about the fact that there's less convergence issues. There's also a lot of literature that has shown empirically, in fact, that they're less prone to being misinterpreted. So for example, p-values don't actually mean that we have a reliable result. And that's a common misinterpretation with p-values that we can avoid. And Bayesian models actually sort of naturally fit our intuition. Where are plausible parameter values? And that also naturally de-emphasizes point estimates. So you have a posterior distribution, you're immediately capturing the fact that this particular slope is not the only one. There could have been different slopes. You have these posterior predictor simulations to generate new data to assess whether your model is actually a data generating model. With the right prior choices, the models are more conservative. But I would say, as damage control, because you're less prone to misinterpretation, even a Bayesian model with default priors by BMRS has many advantages over a model that is frequentist. You get distributions for all parameters in your model, so even for random effect variances, which sort of emphasizes variation more. The model, the package itself scales better to more complex models. You can learn one consistent notation that will capture most of your modeling choices. You don't have to switch packages if LME4 does not support that model. And then I would say it's an opportunity to step outside of deeply ingrained rituals. So this significance testing framework is so ritualized that I think I see Bayesian modeling as an opportunity for us to sort of revisit our primary assumptions about how we do data analysis. To conclude, to me, Bayesian modeling is the sort of natural conclusion of the parameter estimation journey that we've already been taken. And if you're interested in the sort of stuff that I've talked about, so this tutorial on Poisson regression together with Bürkner is also a good introduction, a very easy introduction to BRMS and generalized linear models. So a lot of the stuff that I've talked about today would be covered in this tutorial. And I recommend you the independence and generalizability paper with Martin Grice, which is more about mixed models in general across different areas of linguistics. And they're available under this link tree that I will also post in the chat. So this link tree basically gives you links to these papers. And so with this, I want to say thank you for listening. And I hope that you're more motivated to do Bayesian data analysis if you're not so already. And I hope that you found this useful and insightful about sort of getting excited about Bayesian data analysis. Okay, thank you.